control here. 0.176. All right, 0.176, that's that bit, and add 0.3 to it is 0.476. Okay, we've got that. Now, 0.8 minus C over H. C was not good.
What was C was 1.
C was 1, C over H is 1 over 2. So 0.8 minus a half. Go away. All right, 0.476, let's scribble like that, scribble like that. 0.8 minus a half is 0.3. 0.3. And 0.5 times that, and 1.3 plus all that. So what's 0.5 times 0.3 times 0.476? Sorry?
I hope it's 1.37.
1.37 does sound plausible to me. Okay. CPN equals 1.37. All right, I'm going to start a new sheet so we don't get lost zooming in and out. And we had CPN equals 1.37.
Peter,
Okay.
did you
Yep.
get that table from for the formula?
That was from table B2, bracket A. Okay, and we remember from the previous page that C shape was CPN times KP. Okay, we've got that. We start to need to find KP. KP is defined in clause 1.4, B1.4, sorry, where it says, for freestanding hoardings of walls, the net porosity factor KP should be calculated in equation B1, which is KP equals 1 minus, in brackets, 1 minus delta squared, where delta is the solidity ratio of the structure, surface, or open frame, which is the ratio of solid area to the total area of the structure.
Yeah, okay.
Yeah, I know. I'm sorry. A lot of these sentences you have to read 3 times. Okay, I do that a lot. You go, what the hell is that about? If the solidity ratio is fully solid, then delta is 1, so it's 1 minus 1 squared, so Kp equals 1. Kp equals 1.0 solid. And that is clause B1.4. All right. If we had holes in this structure, if it was 50% holes, our Kp would be half. Actually, no, our Kp would be less than 1. Let's go with that. Okay. Sorry?
Just got the legs and there's nothing.
Right, now we are talking, we're just talking about that bit at the moment. We haven't done the legs yet.
Okay.
Okay, so we'll do the legs as a separate thing. So we're talking about the solidity of that bit.
Yeah.
Yeah, good. So, C shape
1.37.
equals 1.37, happy days. And therefore our pressure on our sign, P is going to equal 0.5 times 1.2 times 1. Sorry, let's do our wind speed. What was our wind speed? 34. 34.03 squared times 1.37. What does that equal? What did you get?
27.97.
I'm going to go for no.
I
No,
used
it's
the
not.
brackets, sorry.
I got 950.
950. Yep, that sounds about right. Now, can you take off that CPN for me and just go the 0.5 times 1.2 times 34 squared.
Oh, I forgot.
Which is six-
Ah, gotcha.
693.6.
693. 694. Remember that this is wind speeds we're talking about. Decimal places don't really, like this 34.03, I just take 34, okay? It's not gonna make much difference. All right, here's a wind calculations hack. Work out what I call the basic pressure, which is the 0.5 times the 1.2 times the V squared. Because that number just gets multiplied by the shape, and often you do a wind speed, you do have a lot of different shapes to multiply it by, so you just keep multiplying by 694, okay? All right, now the upshot of that is our pressure in pascals. Okay, so I'm going to start a new page. What was it again?
Which one?
The bigger number?
951.9.
951.9?
Yep.
952 pascals. Okay? And there is our sine. Okay? And that is 1 by 1.5. And that whole thing is 2 meters tall. All right, what's the force on that?
Force over area.
Yes, so the force equals the pressure times the area, which equals 952. 952 times 1.5 times 1, which is times 1.5. And what does that equal? 1428 newtons, which is 1.43 kilonewtons. Okay? That is the force acting on the sine. So when you come to work out how strong these legs need to be, if I do a sine from the other direction,
Yeah, it's really this is the process. Yeah, really. So I think maybe I should just go to bed and come in.
if you were to reduce that whole area to a single point, where would it act?
The middle.
Yes, in the middle of the sine, so that is effectively right there. Okay? So, right there, the height of that is, that was 1, so that's 1.5. So that's 1.5 above the ground. So the bending moment at the bottom is m star equals 1.43 times 1.5, which equals 2.15 kilonewton meters. Okay? The bending force at the bottom of the leg of the sine is 2.15 kilonewton meters. Now that's held by 2 legs. So each leg is 1.08 kilonewton meters. Okay? Now, from earlier today, we had, you remember, R star had to be less than, phi R U naught.
Yeah.
Okay? That is the 1.08. You need to choose a pole for this sine which can handle at least 1.08 kilonewton meters, and your sine will not fall over.
Well, that was just a fine art. Jesus. Nice.
Or you can just go down to the shop and go, yeah, 40 mil one, that looks all right, I'll get that one.
Yeah, that's
Alright.
what I'm doing.
Is there like a standard that says
what materials will hold that force?
You can do this out of any material you want, okay? Steel poles, I'll show you design tables where all kinds of steel round poles, they'll tell you how much bending moment they can take.
Yeah.
Aluminium, it's a lot weaker,
Yeah.
so you're gonna need a different size.
You lost me.
Timber, there's a whole bunch of different sizes of timber. So yes, there's a whole other code for timber design. We can spend another 3 hours and we can work out what size timber pole you need.
Yeah.
All right.
Just go steel.
Yeah, but be careful of the trap who says steel is stronger, I'll use it. Steel's not stronger. Like as a material per square centimeter, yes, it's stronger. But like a steel pole this big or a timber pole that big, which is stronger? Not really sure. Could be harder. All right, do you remember when I said idiot load?
Yes.
Okay. That's 1.43 kilonewtons pushing on this middle of a sign, which is about 140 kilos. Okay. That actually is pretty solid thing. Do you reckon a group of teenagers could do worse than that?
Yes. Yeah.
Couple.
Maybe, okay. So this is what I call the idiot load. The idiot load is swinging on the sign like this, and his friends are pulling that way, and maybe they can get 200 kilos. So 200 times the height of 1 meter, that might then become the design load. Okay, so I'm not sure what's more critical, the idiot or the wind, but that's the wind force pushing on this thing. Okay, that's the M moment to resist what that is. And so you also need to design your foundation so that it's got more